Assalamu alaikum. Welcome to lecture number 30 of Digital Signal Processing. This lecture is the last lecture of recorded series of digital signal processing as far as theory is concerned. The lecture content for this lecture is to calculate the Z transform for signal. As we learned the importance of Z transform to analyze any discrete time system or digital system in previous lecture, so now we are more interested in the technique and procedure that how we can calculate Z transform of any signal. Here you may notice that I am calculating Z transform for signal, but in the previous lecture we said that Z transform is used to analyze and design any discrete time system, but here it is written as signal. So I must clarify this. Basically we analyze or any system with the help of its response, or in other words we analyze any system with the help of its output signal. So on the basis of its response or output signal, the behavior of the system can be analyzed. That's why Z transform is applied to the output or response of this signal to determine the behavior of the system. So we actually calculate the Z transform for response of the system to tell us about its nature. So in this lecture we are going to learn in detail how we can use Z transform to determine the nature of any signal and what is the mathematical procedure to apply Z transform to any signal. In this lecture we will discuss how we can apply Z transform to a finite duration signals. And in finite duration we have these three classifications which we already know and studied in the previous lectures. Finite duration signal can be causal signal, it can be non-causal signal, and it can be anti-causal signal. So whatever the nature of signal is, as far as it is finite duration signal, how we can calculate it Z transform, we will learn under this topic. After that we will discuss how we can calculate Z transform for infinite duration signal. Here it is the mathematical expression to transform any signal which is given in discrete time domain into Z domain. Here you can see that x of n is the discrete version of any signal, and here we use summation sign because discrete values are being summed after multiplied with z raised to power minus n, and n is varied from minus infinity to plus infinity depending upon the values of n which is given in the provided signal. So this is basically the mathematical expression that will be applied to any discrete time signal to convert it into Z domain. The value of index n can be started from 0 or to any other value, may be negative or positive, but in general we can say that n can be varied from minus infinity to plus infinity. It can start from 0 or any other positive value or any negative value depending. It may be a causal signal, anti-causal or non-causal signal. So general expression of Z transform is basically covering all these three classification. in which the indices is varying from minus infinity to plus infinity. By applying this mathematical expression, we will move into the Z domain. And you all know about this Z domain and its plotting as we discussed in the previous lecture. Another important thing related to Z transform is the region of convergence, which is basically the set of values of Z for which this expression provides an infinite sum. It means we have to look for all the values of Z for which this answer or this expression produces some finite magnitude. If, for example, at some values of Z it is producing infinite magnitude, then it comes under out of region of convergence. If the value of Z results in the magnitude of xz as a finite sum, then it is under the region of convergence. And for example, if for any particular value of z or for multiple values of z, this expression will give us infinite magnitude, then it will not come under the region of convergence. So we will consider only those values of z for which this expression will give us finite magnitude. So it is important to note that when we solve or take z transform for any signal, we have to also define the region of convergence, because without defining region of convergence, the answer is incomplete, as it is defining the values of z for which this expression produces a finite sum. So whenever you will try to solve any numerical which involves z transform of any signal, you must define region of convergence with it. We will see it with different examples, that how we can define region of convergence, how we can calculate x of z of any signal, how we can define its region of convergence, and how region of convergence can vary from question to question, or maybe it may be some standard value for some particular signal. We will see it with some numerical examples in the later slides. So moving on with the numerical example to calculate the Z transform of any signal. First we are considering finite duration signals, and in finite duration signals we can have three classification. First one is causal signal. As you all know, causal signal are those which exist for positive values of time. So for this type of signal, which is given in this slide, x of n is 12057 and indices lie at the first sample, and for this sample we have to determine x of z. So first we analyzed this signal as a causal signal. Then we have to apply the standard mathematical expression to this signal. We will apply the same mathematical expression whether the signal may be causal, anti-causal or non-causal. But for your understanding purpose, I separate out the three signals so you may understand the transformation of causal, non-causal and anti-causal signal into Z domain. Procedure remains the same, strategy will also be the same, but the only difference is the arrow position or indices present in the signal. So if it is also asked in the question whether it is a causal signal, non-causal or anti-causal signal, you may also comment on the nature of the signal. So in this signal we can see that n is starting from 0, which is lie at the sample 1. So this is n is equal to 0. Sample 2 is for indices n is equal to 1, and similarly sample 0 is for indices n is equal to 2. Sample 5 is for indices n is equal to 3, and the last sample, which is 7, is mean for indices n is equal to 4. So there are total 5 samples and n is varying from 0 to 4. So the limit of or the summation upper and lower limits are from 0 to 4. So here we put n is equal to 0 to n is equal to 4, and the remaining expression remains the same. Now in the next step we are expanding this expression, and we are expanding this expression from x of 0 to x of 4. As you can see in the slide that I have expanded the expression in this step from x of 0 to x of 4, and similarly z raised to power minus n is also replaced by the same value of n. So after expanding the expression, in the next step we are going to put the actual values of samples which are provided to us in the question. X of 0 is 1, so we have written 1 here. X of 1 is 2, so 2 is written here. X of 2 is 0. Similarly, x of 3 is 5 and x of 4 is 7. And along with that, we also put the corresponding values of n as 0, 1, 2, 3 and 4 along with these coefficients. In this expression, you may notice that some values can be eliminated or simplified further. For example, this 0 can be eliminated and this z of 0 can be replaced by 1. So in the final answer we can write x of z is equal to 1 plus 2 into z raised to power minus 1 plus 5 z raised to power minus 3 plus 7 z raised to power minus 4 is the simplified solution of z transform of the provided signal. Now again, important thing is to write the region of convergence for this expression. As you can notice that when you transform this z raised to power minus 1 to the denominator, which is 2 over z raised to power 1, and similarly for this 5 into z raised to power minus 3, when you transform this z raised to power minus 3 into denominator, then it will become 5 upon z raised to power 3, and similarly the last term 7 into z minus 4 will become 7 over z raised to power 4. So now you have to look for those values of z for which this expression become infinite, or for which this expression will yield infinite result. So except those values, all values comes under the region of convergence. So it is very interesting and easy technique to determine the region of convergence. Just try to find out the values for which this expression will give you infinite answer, and except those values, all values comes under the region of convergence. So when z comes to the denominator, you know that when z tends to 0, then 2 over 0 will become infinity. Same for 5 over 0 will become infinity, and 7 over 0 will become infinity. So except z is equal to 0 for all values of z, this expression will give you finite answer. So region of convergence for this expression will become all values of z except z is equal to 0. I hope you are getting my point. For further clarification, I included example of anti-causal and non-causal signals. Let's move to these examples. Now in this example, I have considered anti-causal signal. You may notice that the sample values of signal are exactly the same as in previous example, but here the major difference is indices lie at the last sample, which is 7, as shown in the bold. As you all know, the bold term or bold sample is representing the arrow position, or if it is underlined, then it is also denoting the arrow position. So for this question, the arrow lie at sample whose value is 7 and which is the last sample. So by looking at the signal, we came to know that this is anti-causal signal, as well as this is finite duration signal because it has limited number of samples. So for this type of signal, we again have to convert it into Z domain. So we have to apply the same strategy and same mathematical procedure to calculate its Z transform. First, you can see we have written the standard mathematical expression to calculate Z transform of any signal. After that, we have to put the value of n. So it can be taken from the question. As you can see that n is equal to 0 lie at the last sample, which is 7. Before that, n is varying as n is equal to -1, -2, -3, -4, and so on. So it is clarified that n is varying from -4 to 0. As you all know that n can be of any negative value as well as of 0 value because it is an indices position, or it can be a positive value. As it is a anti-causal signal, so n is varying from negative infinity to 0, and for n is equal to minus infinity, the exact value is n is equal to -4, as it is a finite duration signal. So we extracted the value of n from -4 to 0 from the given signal, and we put these values in the standard expression. After putting the values, we have to expand this expression. You can see in the next step we have expanded the expression. The expression is expanded from -4 to 0. The first term is x of -4 into z raised to power minus of -4. Please look at very carefully. One negative sign is from the standard expression, and the -4 is actually the indices value. You have to take a lot of care while solving this because a simple negative or positive will change the entire answer and region of convergence. So we have to take great care of signs while solving the question. So that's why I put the -4 in bracket, so you will not do any mistake while solving the problem. Again, the second term is x of -3 into z of minus, which is of standard formula, minus, and again in bracket I write -3, which is the indices value. So in this way the remaining terms are expanded, as you can see in the slide. Last term is found to be x of 0 into z0. After expanding the expression, now we have to put the values of sample given to us in the equation. So we have put it the value of signal given to us in the expression. After putting the value, we came to know that few terms can be eliminated and simplified as well. As you can see, the coefficient associated with z square is 0. So it means this term can be neglected. As well as the last term, which is 7 into z raised to power 0, is actually 7, as z raised to power 0 is 1. So we have to write the answer in the simplified form, which is written in the last step. And the z transform for the given signal is found to be z raised to power 4 plus 2 z raised to power 3 plus 5 z plus 7. Now again, the most important thing, we have to define its region of convergence. Again we have to apply the same technique for finding the region of convergence. We have to search for those values of z for which this expression is producing infinite sum. So by simply analyzing the expression, we can say that if we directly put z is equal to infinity, this expression will turn to infinity. Otherwise, we can put any value of z and this expression will yield us finite answer. So in this way, we determine the region of convergence, which is found to be all values of z except z is equal to infinity. So I hope that from these two examples of causal and anti-causal signal, your concepts are now much clear related to Z transform. For your practice, I want you people to transform this signal into non-causal signal by just transforming the position of arrow from 7 to any value in between. By that you will reflecting this signal as a non-causal signal. Then apply the same procedure to calculate the Z transform. And interestingly, when you calculate the region of convergence for that non-causal signal, it will found to be all values of z except z is equal to 0 and z is equal to infinity, because it has both the flavors of causal signal plus anti-causal signal. I hope you are getting my point. Now move to the another type of signal, which is infinite duration signal. How we can calculate the infinite duration signal Z transform? As for finite duration signal, there are few samples given to us. But for infinite duration, how we can actually expand the expression? So for that, we have to look at the later slide. So it is very interesting to note that for any infinite duration signal, which is also provided to you in this example, such as x of n is equal to alpha raised to power n into u of n. And you can imagine, if you put any value of n and vary n from some values from negative infinity to positive infinity, then it will yield infinite duration signal. So this is the expression of any infinite duration signal, and you can find the Z transform of that type of signal with the help of this standard notation, which is given to you in the slide. If this type of signal is given to you, alpha can be of any value. You have to just write the answer in this form: 1 over 1 minus alpha into z raised to power minus 1. And if alpha is given to you as 2, you will write 2 in the expression of the z transform. So it is basically the result of one derivation. So if you are interested, you may look at the derivation which is solved in the book, and after deriving the complete mathematical expressions, we ended up with this final answer. So I actually, for your convenience, put the final answer of calculating the Z transform of any infinite duration signal which is causal in nature as this. So you don't need to solve the entire solution, you just use this result if such type of signal is given to you. And for this type of signal, region of convergence is also defined. In this example, if some infinite duration signal is provided to you which is anti-causal in nature, so the general expression for any infinite duration signal which is also anti-causal is written in your slide in the form of x of n, and for that you have to find x of z. The again strategy I have applied for this anti-causal signal also. The final answer or Z transform of this infinite duration anti-causal signal is written, which is same as 1 over 1 minus alpha into Z raised to power minus 1. But you have to note or be careful while solving, because you have to look at the original signal which is given to you, whether it is causal or it is anti-causal. You have to match the form with this form of the signal I have written in this slide. I have highlighted with the pointer. So if this type of form is given to you, then it is the representation of anti-causal signal. And for this anti-causal signal, the final answer is same, which is 1 over 1 minus alpha into z raised to minus 1. But the region of convergence is different, which is mod of z is less than mod of alpha. So you have to also take care while writing the region of convergence. Another interesting example, if infinite duration signal is given to you which is non-causal, which means it has some causal part as well as anti-causal part, as shown in the signal given to you in the form of x of n. So you just use the knowledge of the previous two slides of writing the Z transform of causal signal and anti-causal signal to form this third signal which is non-causal and its transform. You can notice that here beta is not negative, so I have added minus 1 in the numerator. If beta is given as negative, then I don't write minus with the numerator of the second part. And for the region of convergence, I know that for one signal z is greater than alpha, and this for second part or second example, z is less than alpha. And alpha is obviously not the same, or maybe can be the same, but for if the signal is non-causal, then these two terms are the different, which is alpha and second is denoted by beta. So the region of convergence is the limit between these two values, which is z is varying from L. For your practice, I have added an example. One signal is given to you, and after looking at the signal, you came to know that this signal is infinite duration signal and it is causal signal. So we just apply the standard transformation formula, and the result will be 1 over 1 minus half into z raised to minus 1, and half is basically the alpha, which is copied similar as given in the question. And region of convergence is z is greater than mod of z is greater than mod half. Now there are some important properties of Z transform also, such as linearity, time shifting, time scaling, time reversal, and convolution. And as this is the last lecture also, so I want you people to explore these properties, and I will appreciate you people if you search for these properties and will discuss with me in the live session. So it is basically your task to search for these properties of Z transform, study the properties, and come up with some numerical examples where these properties are applied.